first, let's consider finding the relative extrema. So this one is actually going to be the simpler of the two processes just because it has fewer steps. And so, but first, before we even talk about how we find relative extrema, we need to understand what critical points of a function are. And so a critical point of a function is going to be any point that is in our interval where one of these is true. And so first, it could be the case that the partial derivatives of our function f evaluated at that point are equal to 0. And so you'll notice it doesn't matter if we're doing the partial with respect to x or y, either one will work. And we'll actually have to test for both, which I'll show you in the next example. And then we could also have the case where one or both of those partial derivatives evaluated at our critical point does not exist. And so those are going to be critical points that we are going to then test using our second partials test. And so after we have found those critical points, we are then going to use this equation here, which is called our discriminant of our function. And so here you see that we actually are going to have to take some second order partial derivatives of f with respect to x, y, and both x and y. And once we have found the expression for finding our discriminant, we then need to look at what is the sign of our value that we get after plugging in our critical point. And so we have three options. We could get a positive value, a negative value, or 0. Notice that if we get a negative value, we can actually conclude right away that that critical point is a saddle point. Or if we get 0 as our value, our test is automatically inconclusive. So we would need more information than what we have. But if the discriminant is a positive value, we have two options. We could have a relative maximum or a relative minimum. And in order to determine which of these two our point is, we need to also use our f sub xx expression that we find. And so once we've plugged in our critical point in for this expression, if we get a negative value, we're going to have a relative maximum. If we get a positive value, we're going to have a relative minimum. So we only really need this middle column if we get a positive discriminant. And let's go ahead and practice using these steps to find relative extrema. So our first example, we are asked to find all relative extrema and saddle points of the function f of xy equals x cubed plus y cubed minus 3xy plus 6. And so the first step, remember, we're finding all of those critical points of our function f. And to do so, we need to find the partial derivatives of f with respect to x and with respect to y, and then set those equal to 0. So first I'm going to find the partial derivative with respect to x, which is just going to be 3x squared minus 3y. And then finding the partial with respect to y of our function, we get 3y squared minus 3x. Then our next part of this is we're going to set these expressions equal to 0. And then we need to solve for x and y. And so here you'll notice that we actually have a system of two nonlinear equations. And so if you'll recall back in algebra, so 1320, I actually have a resource for this concept on the website. So if you need a refresher, feel free to take a look at that. So solving the system, I'm actually going to use substitution, and I'm going to go ahead and solve this first equation for y. And so when I do, I get 3y equals 3x squared, which then we get y equals x squared. So now I'm going to plug in an x squared everywhere I see y in my second equation. So I get 3 times x squared squared minus 3x equals 0. And so multiplying this out, x squared squared, that's actually going to be x to the 4th power. And then rewrite everything else. I have a 4th degree polynomial set equal to 0. So to solve for our variable x, I'm going to factor. So I can factor out 3x from both of my terms, and then we'll have the other factor being x cubed minus 1, all equal to 0. So now we have the possibility that 3x equals 0, or we have that x cubed minus 1 equals 0. So for this to be true, x equals 0, and for this statement to be true, we get x equals 1. So now I have two possible values for x. We now need to find the values of y when we plug these in. So we're going to plug these values of x in for this equation, y equals x squared, since we already have it solved for y. So if we have that x equals 0, well, we get y equals 0 squared, which is 0. And if we have x equals 1, we get y equals 1 squared, which equals 1. So now we have a critical point 0, 0, and 1, 1. So we have two critical points that we're going to have to use this discriminant second partials test on. So I have copied on our next step the value or the formula for the discriminant. And so first we need to find this formula by finding all of these second order partial derivatives. So when I find f sub x, that means that I'm now going to take the partial derivative with respect to x of f sub x, which we had was 3x squared minus 3y. And we get 6x. When I find the second order partial derivative with respect to y of our function f, that means that I'm going to take the partial derivative with respect to y of our f sub y, which was 3y squared minus 3x. And when we do, we get 6y. And then same thing for f sub xy, except now we're mixing. So now I'm taking the partial derivative of f sub x with respect to y. So the partial derivative of this expression here with respect to y is just the constant -3. So now I can plug these expressions in for our discriminant equation, and we get d equals 6x times 6y minus a -3 squared, which multiplying that all out, we get 36xy minus 9. So now I need to find the value of the discriminant at both of our critical points. So at 0, 0, we get 36 times 0 minus 9, which equals -9. And at 1, 1, we have 36 times 1 minus 9, which is positive 27. So looking at our table, first thing we need to do is identify the sign. So for 0, 0, I have a -9. So because that is a negative value, it's less than 0, I can tell right away from my table that this is going to be a saddle point. So this tells me that 0, 0 is a saddle point. And then 1, 1, I have a positive 27 for my discriminant. So that's greater than 0. So looking at our table, well, now all that does is narrow it down to us having a relative maximum or a relative minimum there. And so to determine which, so now we need to find this extra information of f sub x, x evaluated at our critical point and determine the sign, and then we can see what kind of point it is. So f sub x, x we know is 6x. So plugging in the 0.11 in this expression, we get 6 times 1, which is 6, which is a positive value. So looking at our table, we had a positive discriminant, a positive second order partial derivative with respect to x at our critical point. So therefore, we have a relative minimum. So this tells me that 1, 1 is a relative minimum. And so here are all of our saddle points or relative minimums or maximums for our function.